Hi everyone. In this video, I would like to explain Unit 2 Mechanics of Particles. In this unit, according to our syllabus, the topics are System of Variable Mass, Motion of Rocket, Conservation of Angular Momentum, Conservation of Energy, Collisions, two-dimensional and three-dimensional collisions, impact parameter, scattering cross section, Rutherford scattering cross section, Rutherford scattering formula, derivation, etc. Mechanics. Mechanics means a branch of physics used to study the motion of particles. Generally, the mass of a body remains constant with the time, but sometimes the mass may vary with the time. If the mass of a body or the mass of a system changes with the time, then the system is called variable mass system. Example, motion of rocket. In this video, I would like to explain first two topics: motion of system of variable mass and motion of a rocket. First, system of variable mass. To describe motion of system of variable mass, we consider the motion of center of mass of the system. Center of mass means a point where the total mass of the system may be supposed to be concentrated. The motion of system of variable mass, consider a system of mass m whose center of mass is moving with velocity v bar at any instant of time t. At a later instant t plus delta t, a mass delta m has been ejected from the system and its center of mass moves with a velocity u bar as seen by an observer. Now, the system mass is reduced to m minus delta m and the velocity v bar of the center of mass of the system changes to v bar plus delta v bar. In the first diagram, the combined system is shown. Here m is the mass of the system and v bar is the velocity of the center of mass at any instant of time t. In the second diagram, after a time interval t plus delta t, the motion of the system is shown. In this part, a small mass delta m has been ejected from the system and the ejected mass is moving with a velocity u bar. The system mass is reduced to m minus delta m and its velocity changes to v bar plus delta v bar. From Norton's second law, the force acting on the system F bar external is equal to rate of change of momentum, that is dp bar by dt. For a small interval of time, F bar external is equal to delta p bar by delta t, that is equal to pf bar minus pi bar by delta t, where pf bar is equal to final momentum of the system, pi bar is equal to initial momentum of the system. Considering both the parts of masses delta m and m minus delta m as forming one and the same system, we can write F bar external is equal to pf bar minus pi bar whole by delta t, that is equal to m minus delta m into v bar plus delta v bar plus delta m into u bar minus mv bar by delta t. This equation can be expanded as F bar external is equal to mv bar plus m into delta v bar minus delta m into v bar minus delta m into delta v bar plus delta m into u bar minus mv bar by delta t. This can be simplified as F bar external is equal to m into delta v bar by delta t minus v bar into delta m by delta t minus delta v bar into delta m by delta t plus u bar delta m by delta t. That is equation 1. In this equation, the time into delta t is very small. If delta t approaches to 0, delta m by delta t is replaced by minus dm by dt. Here the notation represents the mass of the system decreases with the time, and delta v over delta t approaches to d over dt, and delta v bar goes to 0. Making these changes, equation 1 leads to f bar external is equal to m into d over dt plus v bar into dm by dt minus u bar into dm by dt. This can be simplified as f bar external is equal to d by dt of mv bar minus u bar into dm by dt. Here in this bracket m is variable. This is equation 2. Equation 2 expresses Newton's second law as applied to a body of variable mass. It is obvious from this equation that d by dt of mv bar is not equal to the external force acting on the system unless the ejected mass comes out with 0 velocity. Equation 2 can also be expressed as f bar external is equal to m into d over dt plus v bar dm by dt minus u bar dm by dt. That is equal to m into d over dt is equal to f bar external plus u bar minus v bar into dm by dt. The last term of equation 3 is rate of change of momentum of the system due to mass leaving it. This can be regarded as the reaction force exerted on the system by the leaving mass. That means from the system a small mass is ejected. This leaving mass exerts a force on the system. That force is called reaction force, that is equal to u bar minus v bar into dm by dt. For a rocket, this term is called the thrust. Now the thrust can be written as m into d over dt is equal to f bar external plus f bar reaction. This f bar reaction is called thrust. Now the second topic is motion of a rocket. This is an example of variable mass system. The rocket is an example of system of variable mass. The rocket consists of a combustion chamber in which liquid or solid fuel is burnt. When the fuel is burned, the pressure inside the chamber rises very high. Due to high pressure inside the combustion chamber, hot gases are expelled from the tail of the rocket. The expelled gases are in the form of a jet with a very high exhaust velocity. Consequently, the rocket rushes in a direction opposite to the direction of escape of gases according to Newton's third law. The motion of the rocket can be explained on the basis of Newton's third law of motion and the momentum principle. In the diagram, a rocket is shown. In this diagram, m is the mass of the rocket, v bar is the velocity of the rocket in the forward direction, u bar is the velocity of gas jet in the backward direction. Let capital M be the mass of the rocket including fuel and v bar its velocity at any instant t in laboratory frame of reference. Let in a time interval dt an amount of mass delta m is ejected from the rocket in the form of gas jet. Suppose minus u bar is the velocity of gas jet with respect to rocket. Then the velocity of gas jet in the laboratory frame will be v bar minus u bar. Let v bar minus u bar is equal to v bar relative. Now the rate of change of momentum of jet issuing out of the rocket, that is force acting on the jet, is equal to dm by dt into v bar minus u bar. From Newton's third law of motion, this is equal to the thrust on the rocket tending to move it in the forward direction. Therefore, thrust acting on the rocket to move it forward is T is equal to dm by dt into v bar minus u bar. Let F bar external be the external force acting on the rocket. Here F bar external is equal to minus mg bar, where mg bar is the weight of the rocket. Then force acting on the rocket in forward direction, F bar resultant is equal to dm by dt into v bar minus u bar minus mg bar. From Newton's second law, the force acting on the rocket is equal to d by dt of mv bar. That is equation 2. From equations 1 and 2, we get d by dt of mv bar is equal to dm by dt into v bar minus u bar minus mg bar. On expanding this above equation, we get m into du bar by dt plus v bar into dm by dt is equal to v bar into dm by dt minus u bar into dm by dt minus mg bar. On simplifying, we get m into du bar by dt is equal to minus u bar into dm by dt minus mg bar. This is the equation 3. This is first rocket equation. Now du bar dt is equal to minus u bar into 1 by m into dm by dt minus g bar. Considering the magnitude of v bar, u bar and g bar, we have dv is equal to minus u into dm by dt minus g dt. That is equation 4. Integrating equation 4 from the beginning of the motion, that is at time t is equal to 0, where the velocity is v0 and the total mass of the rocket is m0, upon an arbitrary time t where the velocity is v and mass m. Now integrating equation 4 in these limits, within the limits, we get integral v0 to v dv is equal to minus u integral m0 to m dm by m minus g into integral 0 to d dt. This gives v minus v0 is equal to minus u log m by m0 to the base e minus gt, or v is equal to v0 plus u log m0 by m to the base e minus gt. This is equation 5. Equation 5 represents the velocity v of the rocket at any instant of time t. This is second rocket equation. Special cases: if the force of gravity is ignored, then v is equal to v0 plus u log m0 by m to the base e, that is equation 6. In the second case, further, if the initial velocity v0 of the rocket is 0, v is equal to u into log m0 by m to the base e. In this way, we can describe the motion of rocket. And by using equation 6 or 7, we can determine the final velocity of the rocket. Now I will discuss the remaining topics in the next video. Thank you.